Hey, howdy everyone. In the previous lectures, we introduced the idea of spatial continuity and suggested it was very important to measure it and to get it into our subsurface or spatial models of any type. We talked about the variogram as a convenient methodology for quantifying spatial continuity. Talked about how it's calculated, but what we're going to do this lecture is get into the practical nitty-gritty details about exactly how do you calculate a variogram given the fact that you typically have sparse data available to you. Well, just a reminder on the variogram definition. For the purpose of variogram calculation, we're going to have to take the average of the square difference between values at a tail location and values at a head location separated by a lag vector h. And all we have to do is take 1/2 of that. Now, I mentioned the fact before that we take 1/2 so that this works out right here, that the covariance function is just equal to the variance, the CIL, minus the variogram value. Therefore, the covariance function is just the mirror image of the variogram function. And we talked about the fact that the covariance function can be related to a parallelogram simply by standardizing by the CIL or the variance. In other words, if the CIL is equal to 1, the covariance function is equal to the parallelogram. So there we go. We got our measures of spatial continuity. Now, in general, we're going to work with the variogram. We calculate the variogram. We model the variogram. We mentioned all of this covariance because within the algorithms we're going to be using covariances, but we'll get into more of those details later on. I think that any new geostatistician, being a geoscientist, data scientist, or engineer, should have at least one experience in their lives where they've calculated variogram by hand. And just doing it today with my class, it was clear that it was a great learning opportunity. Students were making all kinds of interesting mistakes that it elucidated or illustrated their specific intellectual hurdle on the topic. And by working their way through it, I think it was very helpful. So let's do this. This might seem kind of trivial, but I think it's a good opportunity. What I'm going to do is I'm going to give you a one-dimensional data set equally sampled, equal spacing or regular sampling on it. And I'm going to ask you to calculate the variogram for any lag distance you want. You can, since it's regularly spaced, you can pick lag 1, and if you did that, you would be calculating the variogram using pairs going from the first to the second to the third to the fourth, all the way through the data set. And it'd be pretty straightforward, and you'd expect to have kind of a low variogram value, a high degree of covariance. That should happen at a short distance, you'd imagine. Or you could pick lag number 2. You would skip the middle one, so you go from 1 to 3, 2 to 4, from 3 to 5, 4 to 6, and so forth. And you'd work your way through the data set, skipping, going from every possible tail location, but skipping one value going to the next. You could do lag 3 and skip 2. You could do lag 4 and skip 3, and so forth. Just pick a single lag that you would like to work with. So let's go ahead and look at the data set. The data set that we have is shown right here as a data table. We have depth and we have porosity that's been normal scored to have a Gaussian distribution, a variance of 1, and a mean of 0. So the CIL is going to be equal to 1 for this data set as you calculate the variogram. That should help you. The data set is available in an Excel document called 1D_porosity XLSX. It's within, on GitHub, Geostats Guy, the GeoDataset repository. So you should be able to find this data set. Ahead and pick a single lag distance and calculate the variogram for that lag distance. Now note, you should end up with a single variogram value for a single lag distance. So just remember that. That should help you with it. I will show you the solution. I'll walk through it with you in 3, 2, 1. So if you calculate the variogram for all the possible lag distances, this is what you would get. So we got the CIL equal to 1. If we were to pick the first lag, we should get a value somewhere close to about 0.25 to 7, something like that. You should have noticed if you picked a lag at about 1.25 or greater, that you're going to start getting above the CIL. You have a variogram value equal to 1 or even greater than 1, indicating negative correlation. You're above the CIL now. You should drop down again and do this. People might be concerned by this behavior. Well, first of all, this looks pretty okay, pretty typical, right? We have a general increase in the degree of dissimilarity as we have greater distance, and that was one of our observations. We expected that. We reached the CIL, we level out, we got some negative correlation going on here, and then things seem to get a little bit wacky. So what's happening there? Well, if you look at this data set, there's only 10 meters of data. For sure, certainly by the time you're getting to almost 10 meters, like 9.75, you're now comparing the very first sample with the very last sample for one pair. Well, one replicate does not give you a very stable statistic. We need enough samples to have a good representative statistic. So you'd expect that a lot of this kind of strange behavior is probably a result of just having too few pairs. We're comparing the absolute edges of the data set. We're not actually using any of the data in the middle, which is kind of interesting. That's the first observation we can make as far as what's going on with this kind of degree of noisiness. The other thing is that maybe it's possible some of this is information. Maybe if we looked at the phenomenon and we go back here, we look at it, there is a degree of cyclicity. And so this general type of behavior does indicate that there's cyclicity, and in the next section we'll talk more about advanced interpretation of variograms, and we'll talk about that. Now, just in case you were stuck, or if it can help you, here's how I solve this problem. So, I'd calculated for all possible lags. Each one of the columns was a lag. Lag number 1, I would go through and I would do this calculation. Take the difference between the first and the second data. They're all equally spaced. I can just scan through. Take the square of that and put it right here. This will be the second and third, fourth and the fifth, fifth and the sixth, and so forth, right? Just working my way through the data. You got to be careful. You copy and paste it all the way down. You just have to make sure that you stop when you run out of data. And what you'll find is, well, I'll show you as we increase the lag what happens. Once you've got that, all you have to do is take that column and you just have to calculate the summation of it. You calculate the number of pairs that are available to you just using the count command. That's easy to do. And then gamma is just going to be equal to the summation divided by the number of pairs, multiply that by 0.5. That's it. That's all we had to do. Now, the one thing we got to pay attention to, as you pick an increasing number of lag, what will happen is you got a longer lag vector, and you can't go down as far because you're going to run out of data sooner. You're actually reducing the number of pairs available to you. So let's go ahead. We'll pick this one right here. So that's a lag of 1, 2, 3, 4, 5, 6, 7. So by the time I get here, I can't, if I was to copy and keep going, I would be comparing data with nothing. I've run out of data. And so that's why we have fewer and fewer number of pairs available to us, as you can see in the spreadsheet. All right, so that's how you calculate a variogram by hand. I think it's useful to do that at least once in your life. Let's talk a little bit more about the covariance function. We've already explained how the covariance function is related to the variogram. It's a mirror image. The equation for the covariance function is shown right here. This is very interesting because the covariance is in fact equal to the expectation of the average of the product of the variable at the tail location times the variable at the head location. And then there's a subtraction here of the expectation of the tail value, expectation of the head value. And you scan that over all possible locations. Now, first of all, if the mean is stationary, the mean at the tail is the same as the mean at the head, you would expect that this term and this term are just equal to a constant. The expectation at the tail and the head locations is just the mean, and so it's the mean squared. So sample mean squared. So far, so good. You could look at this and realize, too, that if the mean is equal to 0, you could just remove this component, and now we're just dealing with the expectation, or the average of the product between the data values at the head and the tail locations. So that is our covariance function. Now, of course, we're assuming we have stationarity of the mean. We're also assuming that we have stationarity of the variance in order to make this calculation. If we calculate a covariance, we'd realize very quickly it is the mirror image of the variogram. So the red would be a variogram, and the green could represent a covariance function, and it makes sense because you imagine that as you move further and further away, the degree of dissimilarity will go up, but the degree of dissimilarity, which should be maximum when you're very close, or at 0 distance would be the highest covariance, that as you move further away, you would have less and less similarity. So that's relating them to each other. Let's define it formally. The covariance function is simply going to be a measure of similarity versus distance. It's calculated as the average product of the values separated by a lag vector centered by the square of the mean. This term right here. We could say the covariance function really is very much like the variogram upside down. If we assume stationarity, that works out. We will model variograms. We'll talk about variograms, but we'll recognize that inside of estimation and simulation methods that there is the use of the covariance within those methods because of mathematical nicety. And we'll get into that. Let's summarize some of the basic components or definitions that we've really covered until now, but we want to get them really solid, make sure we're using the right terms. The nugget effect. The discontinuity in the variogram at a distance less than the minimum data spacing, often reported as a ratio or as a relative nugget effect, a percentage. Measurement error could be the cause of the nugget effect, and so in many cases or many spatial problems, if there's no expectation of high degrees of discontinuity at distances shorter than the minimum data spacing, we will tend to ignore the nugget effect. There are some spatial problems where you actually do have that type of discontinuity. You want to include it. The CIL is equal to the sample variance. It is the point when we reach the CIL with the variogram. At that point, we have no correlation. We no longer have any information. And if that's important, then we give it a name. That distance, the lag distance in order to reach the CIL, the first instance where we approach the CIL, we will term that as the range. It's the distance at which you no longer have any information. It's also really important because many of the variogram parametric models that we will talk about in the next 2 lectures from now when we talk about variogram modeling, they are parameterized by a contribution, the height, but also by the range, which is very useful. You can vary these models to fit different problems that have different distances of spatial continuity. Now, at about this point in the lecture, as I change gears a little bit, many students get a bit confused because we were talking about variogram calculation, and then suddenly we start talking about search templates, and then we're going to start talking about valid spatial models and about how do we model in full 3D. And they may not realize it's all part of one theme. And the theme is this: how do we practically calculate and model semi-variogram continuity, spatial continuity, from the available and often very sparse information? How do we get that done? And we got problems. The first problem is that we have to calculate the variogram with irregularly spaced data. So we need to use search templates with different search parameters in order to get around that problem. What about the issue of how do we ensure that we have a valid spatial continuity model? And so we'll talk about how we can fit spatial continuity models with a nested, an additive set of spatial continuity models that are known to be valid. The nugget, the spherical, the exponential, and the Gaussian, and so forth. Another problem we have is how do we model in full 3D? We've only calculated the variogram in 1D. How do we move from 1D to 3D? And the answer is that we're going to model in primary directions. Those directions are going to be mutually orthogonal from each other. They're all going to be 90 degrees from each other. And then we model them, and we'll term them as major horizontal, minor horizontal, and the vertical. And then we'll combine them together in a consistent manner, assuming, in general, an assumption of geometric anisotropy. And we'll cover that. We'll get into more details about that. But for now, let's get into how we calculate a variogram with irregularly spaced data, search templates and parameters. In the next lectures, we'll get into this idea of modeling with these spatial models and the 3D and all of that. So, how do we determine what pairs to group together in order to calculate a variogram? Now, in the data set we already worked with, all the data was regularly spaced, 0.25 meters per quarter, a quarter of a meter, and so it was very straightforward. Lag number 1 was 0.25 meters. Lag number 2 was a half a meter. Lag 3, 3/4 of a meter, and lag 4 would have been a full meter. And so we could just scan through the data set. It was very straightforward. But often, we're going to work with, even if we have regularly spaced data, you could specify the offsets as grid offsets. You could do kind of very fast calculations and templates to scan through that. But the diagonal directions get weird because this is 1, this is 1. That distance there is not, in fact, going to be 1. If we were working isotropic, that diagonal direction right there would be like 1.41. And so it gets awkward. We don't exactly have the data at the right distances. So that's a problem. Even for regularly spaced data, we're going to run into troubles about how to determine pairs. Irregularly spaced data gets even worse. The data there might be some average distance separation between the data, but in general, there's no reason why data is going to be specifically exactly at a certain spacing. In spatial contexts and spatial problems, often because of all kinds of constraints, limited sampling and so forth, and sampling to answer certain questions, data is not going to be regularly sampled, and so the distances are going to vary. So, what do we need to do? With irregularly spaced data, we have to make a decision to work with some form of a tolerance. We're going to work with a search template that's full of different tolerances. So let's talk about them one after another. First would be distance tolerance. Now, it makes sense, as I mentioned before, that if our lag separation distance was 200 meters, it's quite possible that the data is in fact maybe 175 meters, maybe 225 meters apart. Not exactly 200 meters. And so you put a tolerance in. You say, well, I'll take plus or minus from this point, plus or minus, let's say 200 meters plus or minus 25 meters, or some type of a distance tolerance. So from a tail location along a certain direction, we'll say this is lag number 3, but I am willing to accept plus or minus a distance tolerance. Okay, so far so good, right? The next thing we need is, well, what's the chance if I'm calculating a variogram in that direction that we're going to have the data perfectly lined up in that azimuth horizontally or that dip vertically? You might expect it, maybe if that was 45 degrees, that looks like it's more like 60 degrees azimuth from north. You would expect that maybe the data isn't exactly on this vector, maybe it's off a little bit. So then you put a plus or a minus on the azimuth also, or on the dip. The result is you now have a distance tolerance, you have a azimuth tolerance, and so you have a space, a template, over which I would consider if there was a tail data point here and a head, any data here within that template would be considered to be within the lag3 bin for that direction given my tolerances. And so that's what we do. We use the tolerances to give us the ability to find pairs in the presence of irregularly spaced data, or in the presence of even regularly spaced data when we want to work isotropically, and we have to account for the fact that we want multiple different directions. Okay. Now you'll look at this template and you realize, well, something's missing here because you don't see these lines just carry onward in this direction. And the reason is that there's another parameter, and that's the bandwidth. And what we're saying with the bandwidth is that we like the azimuth tolerance. We think it makes sense to use, and I agree, it's a good idea. But imagine when we get to lag 20. Imagine just how far away from that vector I would select data because of that azimuth tolerance. It would continue to grow. The further I go out, the further away from that vector. And so the bandwidth says, whoa, I'm not going to go any further than this away from this vector. And it prevents us from mixing information that perhaps comes from very far away from that directional vector just because we're really far out. Okay? It's used actually quite a bit vertically because you can imagine if we had a dip tolerance, we're using a dip tolerance, that what you could run into is that we could start mixing data from different stratigraphic units, very quickly. And so we would consider using this bandwidth to constrain ourselves so we're not taking data vertically too far offset from the current location we're at or current elevation we're at or within our strato correlations, whatever it is, but we constrain ourselves to try to stay within a single unit. Now, of course, we want to model by regions, by groups, and we'll talk about that later. But in general, that's how bandwidths are used. So that's the result of our template. So we take that template, we can position it in our data set and identify all possible pairs. So let's take the example of the fourth lag. The fourth lag is going to be this shape right here. That's the outline of it. We position it on a data value. Now each one of these dots, just for illustration purposes, a nice regularly spaced data set. And so we position our template, and now we're trying to identify this is the tail. What are all the possible head values that could be compared with the tail value for each one of those red circles, that's another pair, tail, head, tail, head, tail, head, that are going to inform the fourth lag bin in this direction. Now, of course, we don't want to just do that. We'd want to move that around to all possible data locations. And as we move it around, we would identify all pairs. So imagine that template is going to scan all the way over all possible data locations. And that would identify all possible pairs within that direction. When you're done, you've taken the square difference of all those pairs, you sum that up, or you calculate the average of it by dividing by the number of pairs, you multiply it by 1/2, and that gets you a single variogram value. 1, 2, 3, 4. That would have been for this lag bin 4. You would have done it for 1 through 3, 5 through whatever, the number of lags you want to look at, and that would give you the experimental variogram. Each one of these points representing a single lag, which is calculated by scanning that template through. Now, we should talk about some of the options, some of the other considerations. First of all, think about data transformations. Now, there's a variety of different transformations you might be interested in. For instance, you may transform your continuous variable to Gaussian or normal, a normal score distribution with a standard normal distribution with a mean of 0, variance of 1, if you're working with Gaussian simulation methods. And so you'd want to do that before you calculate the variogram so that you're consistent with the way that you'll be simulating the variable. You may also transform the categorical variable to a series of indicators if you're using indicator simulation. Or maybe the categorical variable to a continuous centroid for the truncated Gaussian type method. You have to transform the data so that you're consistent with the way that you'll be modeling with the data. Also, you may consider coordinate transformations. The variogram should be calculated aligned with the stratigraphic network. If your stratigraphic network has this types of complexity to it. It's coming up and down. We would have stratal units that are going to be based on a bottom, a datum surface, a top surface, or so forth, and they may be proportional or onlapping. There's a lot we could talk about as far as what type of coordinate scheme. By transforming first the coordinates, we're flattening the coordinates, so now we're working within a nice flat box. When we calculate the variogram, we ensure that we are calculating along the stratal directions, and this is essential because if you just calculate a variogram using the z elevation and you're crossing all kinds of different stratal layers that are coming up and down, you're just calculating right across those layers, you're going to definitely underestimate spatial continuity. You won't get the right spatial continuity model. And then finally, you in fact are going to calculate the variogram. We talked about parallelograms, we talked about covariances, but at the end of the day, what we use within estimation simulation, the inputs into these methodologies will be the variogram. I mentioned also previously that you're going to calculate the variogram in a lot of cases accounting for directionality. You're going to account for the fact that spatial continuity is not the same for all directions. And so how do you find out what directions you should calculate the variogram? Well, first, you can inspect the data. You can look at all available interpretations, check sections, plan views, find out what the paleo flow directions were within the reservoir. Was it a carbonaceous ramp in which you had certain types of paleo environments with different energy levels that were aligned with the ramp margin into the center? There's so many things that can be interpreted by understanding what was going on with regard to the deposition that resulted in that reservoir. So we should be definitely working directly with geoscience expertise, geophysical information, and so forth. Note, if we talk about azimuths, we're talking about angles that are clockwise from the north. And so what are you going to do? Well, you can look at different directions, and then what you're going to do is you're going to try to choose a set of 3 perpendicular directions. So you're going to have the vertical, the horizontal major, and then you have the horizontal minor. And so those 3 directions all together will give you a full 3-dimensional model of spatial continuity. So how can you do it? Well, the first thing you could do is you could first try to calculate an omnidirectional variogram where you don't account for directionality. Use very big tolerances, look in all directions for the same distances. This is often done in the horizontal direction, and you can determine whether or not you even get a well-behaved spatial continuity model that you can try to analyze or work with. If that works, then you could further refine and start trying to calculate the variogram in a major horizontal and the 2 directions perpendicular. In 2D, it would just be the minor horizontal. In 3D, you would add a vertical. You try to see whether or not you're able to actually calculate variograms in those different directions that are consistent with each other. Then what you do is you will then, if you can detect directionality, anisotropy within your phenomenon, you're going to then model all 3 of those orthogonal directions, and you're going to assume a geometric model of anisotropy at all directions in between, at all other directions. And so what does that look like? Okay, so we got y, x, this is a 2-dimensional problem. Through all of our geologic information and inputs, through looking at geophysics, through looking at the data, we identified that the 030, the 30-degree azimuth, is the principal direction. Okay, so this is going to be our principal direction. By default, since we're in 2D, we're only going to then consider the 120 degrees, which is going to be 90 degrees or orthogonal to our principal direction. So that's going to be our horizontal minor. They're both rotated and aligned with each other. We'll calculate the variogram model and specifically parameterized by the range in that major direction. So the range is pretty long. We'll calculate the range in the minor direction, and we'll assume an ellipse or ellipsoidal in 3D range change over different angles. That model is valid. That's a model we can use for spatial continuity. So now we have a full three-dimensional model of spatial continuity by only having to calculate the variogram within the major direction, 30 degrees, and the minor direction horizontally, which is 120 degrees azimuth. And from that, we can fill in all of the other possible directions using this geometric model of anisotropy. And we'll talk more about that in the coming discussions. What are some guidance, what's some information I can give you with regard to variogram calculation parameters? First thing, if we were talking about general guidance, it would be the lag separation distance should coincide with the data spacing, specifically the minimum data spacing. There would be no value to calculate the actual variogram at distance shorter than the minimum data spacing. You don't have any information. There'd be no possible pairs. So in general, that's where we're going to start. The lag tolerance is generally going to be chosen to be 1/2 the lag separation distance. Why do we do that? If this is the lag separation distance from lag 1 to lag 2, if we set 50% of that as the lag tolerance, what happens? We have no gaps in our template. The second lag bin is adjacent to it, goes right up against the third lag bin, and we don't lose any possible pairs. Now, if you have a very noisy variogram, you could increase the lag tolerance, and now you have overlap, which means you potentially have data that would be considered in lag 3 bin and also in lag 2 bin. There would be overlap between the templates for each one of the lags. That's fine. That will cause a smoothing effect on the variogram, make it a bit more interpretable. Default, start at 1/2 the lag separation distance for the lag distance tolerance. So, variogram calculation. Of course, we did it in Excel. It was tedious. We did it so we got a little bit of hands-on type of experience with it. But let's get a little GS Live experience. Now, students will typically complain about this part because GS Live is a set of Fortran executables run by parameter files. You have to run them in a command window. There's no GUI. It's pretty old-fashioned. But GS Live is open source. It's standard. In fact, if you look into many methodologies or packages for geostatistics, for instance, Pyrcz Live is basically just wrapping the Fortran GS Live and putting in Python, which is very useful. Appreciation to the authors on doing that. But you'll find that many applications for geostatistics are actually, in fact, based on GS Live. It's been used in many different places. It's very well tested. It works very well. You have complete expert control. You can build your own workflows. You can do all kinds of neat things with different types of scripting approaches. I've even used Visual Basic to do it. I've scripted it through C++. And in Python, I've actually put together a very straightforward wrapper. It's called Geostats Py. And all it does is it takes the executables, runs them, writes out the parameter files, runs them, takes the input back in, re-implements a bit of the graphics program. So you can put things together in a nice Python script. Only works on Windows. I haven't properly wrapped it. Okay, the main point is we go back to GS Live, we get back to the fundamental tools, and we'll have a better understanding. The method, you have a set of executables with the basic algorithms. You put them together in a workflow. You have parameter files, and they are ASCII files with just the variables, and they'll have comments so you know what each one of those are. And you're going to have and you can edit them, of course, in Notepad, TextPad, or whatever text editor you like to work with. And the data files will be in raw ASCII. They're GeoEAS format. It's a very simple ASCII format for data. And the graphics are going to be in PostScript, which is really nice. They're vector-based graphics, but you'll need a viewer enabled in order to be able to look at them. So this is what it looks like. We have a data file. Our GeoEAS format is shown right here. The name of the file, the number of columns, each with a variable. The name of the columns are listed, and then the data will be either space or tab delimited with the n columns of data, and it will carry on until an end of file, and an empty line will indicate the end of file, and the program will stop reading the data file. The parameter file for a program like GAMV, which is the one we'll use for calculating variograms, we could have used GAM because the GAM program works with regularly spaced data, but I thought it was much more instructive to use GAMV because it's more general to regularly spaced data. But we have our data here. We can go ahead and look at GAM. We tell it the name of the file, which is 1D_porosity.dat. We tell it which columns to look for X, Y, and Z. X, Y, and Z, 1, 2, 3. We tell it how many variables we want to work with. We're only working with simple variograms, none of these cross variograms or anything, so we just have one variable to work with, and that's in column number 4. Trimming limits in case we want to remove bad data, data that's out of bounds somehow. We have null values. You'd use the trimming limits here to remove it. The file for the variogram output will be called gamv.out. The number of lags. Okay, this is going to all should make sense based on what we just talked about. Lag separation distance, 25 meters. That makes sense. Lag tolerance, 1/2 lag separation distance. So far so good. Number of directions. We got a 1D problem. There's only really one direction to consider. And then the azimuth, that doesn't matter because we're going to be working vertically. You'll notice that the X and the Y are all equal to each other. It's only the Z that changes. So it doesn't matter. We'll just say 0 azimuth, 90 degrees azimuth tolerance. We're not concerned. It's really isotropic in the horizontal direction now. And we'll put the bandwidth doesn't matter here. But we'll say the dip is 90 degrees. The azimuth tolerance is 22.5. They're all in the same line, but we just put some tolerance just in case. I didn't want to put 0 and then have it all determined by some floating point error or something. So I put a little bit of tolerance. And the bandwidth, I put a little bit of bandwidth so that it's not going to be, so it won't go far away. But here the problem is completely vertical, so we shouldn't be too worried about that. So in fact, what we're investigating is a cone and then a cylinder going down the well. Then the number of, do we want to standardize the sills? Well, the data set already has a variance of 1. We should be fine. The number of variograms will be just 1 variogram. It's going to be 1 variogram type is just a traditional variogram. And the head and the tail variable is only going to be variable number 1. We only have one variable we're working with. It's just it with itself. The output file would be the semi-variogram lag number, the lag distance, the variogram value, the number of pairs. This is important because if you have a point that has no pairs, you shouldn't include it. And then the mean of the tail and the mean of the head, so you can check whether or not you have a stationary mean for that one. So we go ahead, we can use that information, we can go ahead and try to run GeoSlib. And I think just like calculating a variogram by hand, it's useful to run GeoSlib at least once in your life to understand what tools are available to you. You may want to just put a workflow together very quickly. You can do it with GeoSlib. I have put 1dporosity.dat on GitHub, and so that's available to you. It is located at, well, I had it in a previous slide. It's located in my geodatasets repository, so you can download that. We'll fill out parameter files for GAMV PAR, which is the Variogram Calculation program for regularly spaced data, and vargplot, which is Variogram visualization given the output from GAMV. And we'll make sure we have the GeoSlib executables gamv.exe and vargplot.exe, which are both available in Windows and Linux. They're available on the internet. You just type in GeoSlib, you'll find it very quickly. They're available on a website there. I forget what it was called. So let's go ahead, and I've set that up already, and we'll do it very quickly. And so I have my example in a working directory right here. I have my 1D porosity data that I downloaded from GitHub right here. No surprises, I opened it up in TextPad. I have the gamv.par, and I've already talked about those parameters, the different types of variograms. We're just doing a traditional semi-variogram. And I have the vargplot program, which I'm just telling it that I have one variogram to plot. I tell it what distance limits are, the title, and how to put dashed lines, dots. It's experimental variogram, so I want to be dots. Now all I have to do to run this is I just have to get a command prompt. I'll come right here, open up my command prompt, and I just have to type gamv. Now, if I run this, it's going to assume gamv.par in the working directory is the parameter file I want to run. I could do this, and now I'm telling it, gamv program, use the gamv.par parameter. That's pretty useful if you're scripting with a batch file or something. You can have a bunch of different parameters, run them in sequence. So I ran it. I got a little bit of summary statistics from the data set. Yes, the variance is pretty close to 1. I might have thought about standardizing it because it's not quite 1. It's not perfect. It's not enough data to have, once again, the belief in the law of small numbers. A small number set isn't going to exactly have the representative statistics of the population, which with the transform should be 0, 1, 0 mean, 1 variance. Here we're off by a little bit. It's about 96.96 instead of 1 for the variance. Okay, so we just ran that. What came out of gamv was this file right here, which we showed before. The variogram lag, the lag distance, the variogram value, the number of pairs. And so this is pretty useful. You can look through it and see number of pairs and so forth. Next, to visualize it, we just have to run the the vargplot program, And once again, you could do vargplot.par, or you could just run vargplot. And if the name of the parameter file is vargplot.par, it will just default to look there. Now, if you don't have a parameter file and you run the program, in fact, it will, if you delete the parameter file and you just hit vargplot, and you get to, vargplot, and you get here, if you had no parameter in the no parameter file in the working directory, it would generate you a fresh blank parameter file that you could then populate. Okay, so we already ran that. I already have Ghost View, a good old Ghost View installed on my computer. That allows me to view PostScript files. And so if I open it up, I get something like that. And of course, you might look at that and say, well, you shouldn't really have the lines on it because it's an experimental variogram. It's not in a variogram model. And so we should get rid of those lines. And why were you doing that? So I could come over here, lines 0, 1, and I put a 0 there. And just to prove that, in fact, I am running this, I can go ahead and, I'm sorry, I have more than one command window. I had to find it. And so I could run it again. And so you see a 0 there now, so the parameter should have changed. And I can go back and open that up again. And there. Now, you might say, well, I want to see all those points. We could increase the y-axis. That's one of the parameters. We could look further. We could calculate more lags and so forth. But this is a very straightforward way to calculate a variogram. So once again, I invite you to take that data file, go back and rewind to the parameters I used if you need help, and go ahead and try running GeoSlab. I think it's good to just try it out. So if you run it, this is what you should see. I did a little bit better job of tweaking the parameters to show all the points. But this is what we'd see, this original data set, and this is what we'd get. And so we could talk about how we'd interpret it, that we have a range of about 1.5. We have some type of cyclicity or trend, but we'll get into those details. So I think it's useful to try an example of calculating or estimating the best variogram search parameters for these 3 situations, 1, 2, and 3. And so based on our previous discussion, go ahead and pick some search parameters that you would use for each one of these, and I will walk you through my recommendations in 3, 2, 1. So the first one's pretty straightforward. We want to calculate the variogram isotropic, the lag distance or the lag size. Look for the minimum data spacing. It's isotropic, so I don't care what direction. Just look at pairs that are close to each other. And I'd estimate that's about 50 meters apart given these axes. So about 50 meters. The lag tolerance should be about 1/2 that. And the data extent is 500 meters in this direction, 200 meters in that direction. So we could really only go up to about 1/2 that maximum extent and really have reliable variograms. So about 250 meters. Well, 50 meters for each lag. We can go 250 meters. We can do about 5 lags for 250 meters. The horizontal bandwidth, I'm not really going to be concerned about bandwidths in this situation because I'm working with an isotropic variogram. I don't care about trying to limit the distance offset from a vector because with an isotropic variogram, I'm only concerned about distance. I'm not concerned about directionality. The azimuth could be any because I set the search tolerance to 90 degrees. What does that mean? Well, 90 degrees, well, I'm going 0, the north direction. Then I'm saying go 90 degrees this way or 90 degrees that way. So my tolerance is saying I'm going to search through like this. I'll take all possible values above myself. Now my students, this will result in isotropic, but my students have been concerned about this in the past. They think, why not put 180, sorry. Why not put some number greater than 90? What'll happen is if you're searching in this direction, you put more than 90, your template starts to go back on itself, which means that as you're searching forward, you're going to actually double dip. You will double include some of the pairs just if they have the right orientation to do that. And that'll create a bias. So 90 for an azimuth tolerance for an isotropic variogram. So what about the anisotropic case where we want 45-degree direction? So imagine a 45-degree direction going like that. The data is clustered now, so the minimum data spacing is going to be maybe about 20 meters, our lag tolerance about 10 meters. Number of lags, well, we still have about 250 meters of data in the longest direction, the greatest extent, and so we can work up to about 250. Well, 20 meters for lag, 12 of those, 240. So that's pretty close, so we could do that. Horizontal bandwidth, well, we have directionality. We may want to limit that. It'll depend on the problem, but you could pick something like 200 or so. The azimuth, well, it's a 45-degree angle azimuth that we want to work with, and so 45. And a pretty common azimuth tolerance is about 22.5. That gives you about 45 degrees that's going to be included in your tolerance. If you wanted to get more precise, you had the data to support it, you could try to decrease that. If you don't have enough data, you could increase that to get smoother variograms in each direction. What about anisotropic in the 90 degrees? So now we're trying to go along this bed. It's stratified, so we know that things are kind of changing. We want to kind of focus within a certain area, not mix up data, not mix up information too much. Well, first of all, data is pretty clustered up, about maybe 15 meters apart from each other. Lag tolerance will be half of that. Number of lags, well, look at this problem. It's 300 meters in extent, so we can go about 150 meters in the 90-degree direction, so we get 10 lags at 15 meters each. By putting a 5-meter bandwidth, that does provide us some control to ensure we're not mixing pairs from this stratal unit with this strata unit or that strata unit. It keeps things separate. So we could use a vertical bandwidth in order to impose that. Now we would expect that since we're along the x direction that we want to work in an azimuth of 90. Remember, y would be 0, x would be 90. We could use an azimuth tolerance if this data could be in and out of that section. And so we could put that in based on what our data configuration is, whether or not we need that tolerance. And I make a note here, I just added this in just now, I apologize for excluding this, but we would want to have control over the dip. We're in the x direction, but we want to say let's go 0 dip, so we're traversing along in this direction. So this variogram would be calculated so that we're going along these layers. We would control that by indicating a specific dip to do that. All right, so that was a lot on variogram calculation. So I hope that was useful to you. If you have any questions or comments about this lecture or any other lecture, I'm always happy to discuss geostats. I'm available on Twitter. My email is easy to find. I can also be contacted through comments on these videos right here. So I hope it's helpful. Okay, thank you.